All right. Well, thanks. First of all, it's nice to be invited to this meeting, and actually my first time in Hong Kong, other than passing through the airport a few times. So anyway, it's nice to be able to visit here, and thanks for all the people that have shown up for the talks here. So what I'm going to do I might talk overlap a bit with certainly what Rainer spoke about, and also Serge, but maybe with a little bit different view on things. So one thing I'm going to first get a little bit more into the details. Rainer talked about these entangling gates, and he talked about in terms of stimulated Raman transitions and the Smolmer and Sorensen scheme. But there's another way to look at these things, and it's just a matter of taste how you look at it. But it's a different picture to look how these gates work. I'm going to say one of our favorite topics is atomic clocks, and I'm going to try to give some connections between with the clock development and quantum information processing. And another application that just is, say, force or displacement detection, and I'll give just a couple of examples of that. I'm going to say a little bit about this, how things might be scaled up and the infrastructure requirements, and then I'll give a bit of a comparison with the other technologies that are out there. And with apologies already, these are some very selected examples. There's many other topics I could be including in this talk. Also, I want to say at the outset that Reiner's and our group are not the only ones doing this. This is a list of the groups that I know around the world, and it's probably keeping it updated is a problem, so it's probably not quite up to date. But it gives you an idea of the scale of the interest in quantum information, and this is just the groups working on atomic ions to realize the elements of quantum information processing. So let me what I'm going to start out with is, as I say, a little bit different view of how these quantum gates work. And of course, you know, this picture looks different, but it's entirely equivalent to what Molmer and Sorensen and others described, and what Rainer was talking about in terms of stimulated Raman transitions. And so the picture here is, suppose we consider a phase space diagram for motion of a particular mode in this multi-ion crystal. For simplicity, you can first think about just a single ion on the trap, and we'll consider a single mode along one direction. And the thing we're going to rely on here is that if we displace the wave function, which is given by the green blob there, that we can see how the phase of the wave functions transmits if we consider how the displacement operator works, and we can consider how we can concatenate a bunch of small steps, and in fact, if we arrange the steps so that these small steps so that there's a displacement in phase space where the wave function comes back and is overlapped with the initial wave function, except we find that the wave function picks up a phase factor then that's given by the area enclosed in phase space. And so that's the key thing we're going to rely on. Now, what we want to do to realize an entangling gate is we want to make the forces that give this displacement be state dependent. And for example, one target is to make a so-called pi phase gate, which has the truth table as I've shown here. And these are, we tend to think, when we talk about these quantum information things, this is entirely equivalent to a controlled knot with up to some rotations. And so this gate would be universal in the same sense that a controlled knot gate would be, which was Rainer was talking about. I keep forgetting I got this thing in my hand here. Okay, so let me just start out with the simple picture of how this idea works for single ion. And the basic idea, the way we want to implement these displacements is that what you can think about it for a single ion, if we have a detuned laser beam in a two-level system, we know that this gives rise to a Stark shift. And what we want to do is we want to make this Stark shift have a spatial gradient, which then that spatial gradient, gives rise to the force on the ions, and we want to make this gradient force depend on the state of the ion, either being spin up or spin down. And I'm going to apologize. Throughout the talk, I'm going to mix up and down with 0 and 1, but in either case, we're talking about qubits. So one way to get the idea of what we do is we're going to take two laser beams, and the directions are going to be, for example, as I've drawn here. If the frequencies of the two beams are equal, then what we do is we set up either, well, a combination of a polarization or intensity gradient. So what you want to think about is in the trough sphere, the field is 0, so there's 0 Stark shift, and of course there's a kind of washboard potential that we generate. In this case, it's static with respect to position. On the other hand, if we make the frequencies slightly different, what we're going to do here is make the difference frequency between these two waves coming in different directions to be roughly equal to the motion frequency, but offset by some small detuning. And so the idea is that, again, we want to make the forces on the two internal states different. And just as a simple example, let's assume that they're equal and opposite on the two spin states. So the picture for two ions now that you can think about is, suppose we make so this is the washboard potential that's going to be dragging across the ions. And the key thing is we're going to adjust the position of the ions according to the wavelength so that both ions sit at the same point in this, up to 2 pi in this intensity gradient. And so the idea is then that, and we're also going to think about, of course, with two ions along the axis of the system, there's going to be two modes. One is we call the stretch mode, where they're moving in opposition, and the other one is the center mass mode, where they're moving together in unison. And the two frequencies of these modes are separated by a significant factor. The stretch mode is basically square root of 3 times higher than the center mass mode frequency, so we can spectrally isolate the modes. So what you want to think here is we're going to try to make this detuning equal approximately to this stretch mode frequency. And so what you want to think about, since we've made the forces equal and opposite for the two spin states, in the case when to excite the stretch mode is you want the forces to be equal and opposite on the two particles. And the way you do that then, since we've chosen those forces to be equal and opposite, what that means is for the case where the two spins on the two particles are equal and opposite, then that force then at this frequency near the stretch mode is what can excite it. On the other hand, when they're in the same state, then those forces they excite only motion in the same direction. In other words, they would want to excite the center mass mode, but they can't because we're off resonance with that mode. And so the simple cartoon picture is, let's suppose we've frozen out the motion. This represents the wave packet of the motional mode to start with. And then since we're slightly detuned, if we leave on this force for time that's given by 1 over the detuning times 2 pi, then the cartoon picture of what happens is we leave this force on for a certain amount of time, so the ions when they're in this opposite spin state, they traverse a circle in phase space, and we adjust the conditions such that the area gives this pi phase shift, and this basically then realizes the truth table that we talked about for our gate. And one thing to say is that we can think about this, the net process when we make this loop in phase space, that gives the equivalent of what a Hamiltonian were given by this factor here in the exponent, and more generally than if we have larger number of spins where Jz is the sum of the sigma z's for each particle, we generate a Hamiltonian like this, and so this up to an overall phase shift on the wave function. This is the entangling term that Reiner talked about in his talk. This Jz squared term. So this quantum gate, in fact, it's used as Reiner explained, in simulations to be able to simulate the Ising interaction, for example. Now, one thing to say is we want the force on these wave functions to be uniform, and so what that means in practice is that we want the spread of the wave function to be small compared to the effective wavelength of this standing wave that we run across the atoms. And if the wave function is larger than, say, the wave function, then the forces on the different parts of the wave function are different, and it won't work in the simple way that I've described. So this is basically, although we need to satisfy this condition, the one advantage of this scheme is, as Molmer and Sorensen and others pointed out a long time ago, is that as long as we're in this region of linear excitation, that is where the wave function is of the motional mode is small compared to this effective wavelength, then in fact we don't need to start in the ground state of the system or a particular eigenstate. As long as the wave function is small, then we can carry out get the results of this phase gate that I mentioned. So that's an advantage over the Serac and Zoller scheme, where you needed to start in known eigenstates to carry out that. So that was one of the significant advances that Molmer and Sorensen and others came up with a while back. So anyway, that's a picture, a slightly different picture than what Reiner talked about, but of course they're equivalent in the end. So I'm going to switch gears a little bit and talk about clocks and just how some of the ideas of quantum information processing comes into play when we think about clocks. So, very simple ideas about clocks are that they're very much, the reason for atomic clocks is that, say, a superposition, an oscillating, say, electric dipole, is very much like a pendulum clock. And the nice thing, of course, about atomic clocks is that at least all atoms of a given kind, given species, and if we select a particular transitions, all atoms oscillate at the same frequency, which is the idea of an atomic standard for time. So that, anyway, one picture is you can think about this electric dipole oscillation, say the oscillating electron density versus time. But as a practical matter in clocks, what we typically do is we start the atom in the ground state, and then we apply radiation near the transition frequencies for a certain amount of time. So if it's right on resonance and adjusted for the right time, we completely excite the ground state amplitude into the excited state amplitude. On the other hand, and typically we might not be right on resonance, so we'll get a superposition state after applying the radiation. And so the simple idea of is that basically we measure the probability of exciting, and when the probability is maximum, then that's the condition when the applied radiation is equal to the atomic resonance frequency. And that's the condition we want to realize the atomic clock. In that case, we measure the frequency of the oscillator that's exciting the transition. So in a cartoon picture of that, we have some atoms that we contain in some cell that's hopefully isn't perturbing the frequencies of the atoms very much. And in fact, historically, this is the way some atomic clocks were made using hyperfine transitions. It's basically to have a cell of atoms, and usually the cell was coated with some material of low polarizability, so the internal states of the atoms weren't probed very much. And we could shine radiation on them, and basically we would look for absorption of the radiation transmitted through. And as we set the frequency of the exciting oscillator, we'd get the usual resonance curve. And then when we synchronize the frequency of the oscillator to the transition frequency of the atom, that's the condition we want. And then to realize the clock, we just count oscillations of the oscillator that does the excitation. Now, just one slight thing we need to realize, of course, if we just try to sit right on the top, at the top where the slope goes to 0, we're not very sensitive to small changes in the frequency. So the only thing we do in the lab is we probe on one side of the resonance and then the other, and then we try to realize the condition where the response is exactly the same. Under that condition, then the mean frequency of the two probe frequencies gives the center frequency of the transition, because we can, in most practical cases, the line shape is very symmetric. So that's literally, in almost all cases, how the clocks work these days, is that we do this probe on both sides of the line and then measure the mean frequency. So let me say one picture of how this works. We often try to use Ramsey spectroscopy. We could leave the radiation on continuously, but there's some advantages of doing this Ramsey technique, where we use 2 pulses of radiation to probe the atoms. Excuse me. So the idea in Ramsey spectroscopy is we'll start out with all the atoms, say, in the ground state, the spin indicated by spin down here. And then we apply the radiation. We first do a pi/2 pulse on the atoms. We wait some precession time, and then we apply a second pi/2 pulse. And then we measure the number of atoms that are, say, promoted from the ground state to the excited state. So where P up represents the probability of each atom being excited to the upper state. So that if we follow along here after this first pi/2 pulse, then we create an equal superposition on each atom. So we have this product state of the spin of the superposition states on each atom. And then after the free precession time, if we're not exactly tuned to resonance, oh boy, right in the middle of this thing. Anyway, but the basic idea is we can factor out an overall phase shift on the wave functions, and the idea is that the up state in this then picks up a phase factor for each atom, such that this phase is given by the difference frequency of the probe and the atom times this free precession time. And then when we measure this, in this idealized example, when we finally measure the states of the atoms, the probability, average probability of each atom being in the excited state is given by this expression. So what about, how do we think about signal to noise in these experiments? So the signal in this case is we want to be sensitive to small changes in the frequency of the probe oscillator. Excuse me. So the signal is basically we want that sensitivity to be maximum. So we want to be on the point of maximum slope. So the way we think about the signal is it's just the derivative of the number of atoms that are projected to be in the upstate versus the frequency difference, basically, given by this overall phase. And in fact, mathematically, this turns out to be this expression here. Now, the noise in the system, when we measure when we measure each atom, we can, if they're all in the excited state, then in fact, the fluctuations in this idealized case go to 0. Similarly, if they're all in the ground state, the noise goes to 0. Say when we're at equal probability, or more generally, when given any probability for being in the upstate, the fluctuations, this is just given by the binomial distribution, and so the fluctuations in the of the measurements over all the particles is given by this expression here. So the signal to noise gives this very simple expression. It's just given by the square root of the number of particles. And the thing, one thing to say too here is that it turns out that in this simple analysis, it's actually the signal to noise is actually independent of where we're sitting on this curve, but in fact we don't want to be measuring up here because there may be some added noise to our signal, and so we want to dominate the noise by the noise just in the atom measurement noise. In fact, we often call this the projection noise because basically, for example, when we're sitting right on the side of the resonance, that means that each atom is an equal superposition of up and down, and so each time we measure the atom, it's either, when we project it, it's either going to be in up or down, and the fluctuations on those measurements is what we might call this quantum projection noise. That is, it'll on average, it'll be the probability to be 1/2, but the noise is given by the fact that each time we measure, it'll be either up or down, not in between, and we have to worry about the fluctuations on those each time we measure the particle. So anyway, it turns out actually for Ramsey spectroscopy, there's a very simple expression for how we usually think about the noise. The relevant thing for the noise is we want to consider the fluctuations of the frequency given by the prescription of how we measure the frequency, normalized to the oscillation frequency. And this is the measurement which we usually, in the atomic clock world, we call actually it's called the stability for historical reasons, but it's actually a measurement of the instability, and we want to make that small, of course. But anyway, for Ramsey spectroscopy, it turns out there's a very simple expression that gives this statistical measurement precision. It's just this very simple expression up here, where this is the transition frequency, this is the number of atoms, this is the free precession time in the Ramsey method, and this is the total averaging time. That is, of course, much longer than the free precession time because we repeat this measurement over and over. And of course, this expression, assumes no dead times in the experiment. So it's clear. The other thing to say is, in the atomic clock world, we want two things. We want to maximize the signal to noise. In other words, minimize this fractional statistical error. And the other thing is of course, we want to control the systematics very well. I'm not going to say a lot about systematics effects, except that it's both of those things we want. And so from this expression here, obviously, we win a big way if we can go to high frequency. We'll also win by going to big numbers. And I'll say a few words about that. And of course, we want very narrow transitions where we can make the the free position time as long as possible. So I'm going to give you one example from our lab. And so we knew this for a very long time. That is, you'd like to go to high frequency for the reason I've just explained. But there were problems. First of all, at least when we started thinking about this decades ago, the oscillators that provided the radiation, ideally we'd like to go to laser frequencies, but they weren't very stable. And the other thing is there was no way to measure the frequencies, or at least a convenient way to measure the frequencies. But anyway, nowadays we all think about going to optical transitions, at least in the standards lab. So this is an example from our lab where this is the transition frequency of this S to D transition in mercury 199. Of course, the nice thing about mercury and other atoms and ions is that for these in this case quadrupole transition, the resonances can be quite narrow. Actually, this idea of optical atomic clocks, I like this thing that this fellow used to be at NIST dug up in the literature, and basically this idea of optical standards, optical clocks, goes back quite a way. And so there's this text that he found that basically by Lord Kelvin and his colleague Tate, that they came up, they gave this idea was attributed to Maxwell, and you can read it there. And basically, I think what this passage is saying is that, they say use natural standards that are reproducible, like atoms of hydrogen or sodium, so they're all alike, and so that you can use these vibrations, which I'm quite sure they were talking about optical vibration in that case. Anyway, it's known to be, absolutely independent of position in the universe. Now, they can be excused because at that time they didn't know about relativity, but the idea is of course there. So anyway, I'm going to give you an example from our lab. And this is, we started out thinking about optical clocks. This goes back to 1982. And anyway, we were thinking that we were starting to play with mercury atoms. And I'm going to talk about it in two contexts. I'm going to talk about this transition as both a reference for a clock, but also it makes a qubit being a two-level system. It's not the best qubit, it turns out, but the ideas are about its how it could be. The qubit is simpler to describe than some of the other transitions we use. So the idea is that we can make superpositions of the state. As I said, the state lives, or indicated on the last figure. The upper state lives about 1/10 of a second, which is not infinite, but most of the experiments, certainly on the quantum side, last on the order of a millisecond or so. So we can think about this being long-lived. Anyway, what we can do then is we can prepare the atom in the ground state. We drive the transition for a certain amount of time, and then we make a superposition state. Now, how do we measure this? The idea is if we've made this superposition state, then we can drive this strongly allowed transition, and this is the one we use to do Doppler laser cooling. But anyway, the idea of the measurement then, this projective measurement is, and I think both Serge and Rainer described this, but just to briefly say it again, is that after we've made this superposition, if we turn on this radiation here, which does laser cooling and also provides fluorescence, if the atom is projected into the ground state, then we can make the atom scatters, and we can pick up some of that radiation in a phototube. On the other hand, by repeating the experiment, and then turning on this laser again, if the atom is projected up here, there's basically no scattering, and the net result is that when we get this very discrete signal when we probe with the blue laser there, the atom does the cooling and the projection is that basically when the atom's in the ground state, we see fluorescence. when it's in the excited state, we see very little. This is just background. And the idea is, of course, we can put a discriminator right there, and with essentially 100% efficient, we get this very high efficiency state readout. And this is basically, this also kind of gives the idea of the projection. If we make unequal superposition, we never measure fluorescence in between. We either the atom is projected into the D state or into the ground state. And this is again, sort of a visual a way of seeing how this projection measurement works. So in fact, Jim Berquist was the one who really, he's always been the laser expert in our lab, and he led this effort to make a clock. And the only reason I wanted to acknowledge him here is basically we knew when we started on these experiments in 81, trying to realize this, first a microwave standard based on mercury, but then we were also always thinking about this optical transition. Of course, cesium was getting better and better, but this, anyway, around 2006, this work led by Jim Berquist was finally able to get the precision where at least the systematics effects were, for the first time, lower than you could get in a cesium clock. And in some sense, this marks when kind of the conversion to where everybody, I think, jumped on this side. Well, people were thinking about it before this measurement, but it was clear the optical clocks were going to be better in the long run. So why, in our experiments, why you say, well, why one ion? We could win by increasing the number, the square root of the number in terms of signal to noise, as I indicated earlier. For mercury, one reason is that if we have two mercury ions in the trap, the inhomogeneous electric fields from one ion acting on the other interact with the quadrupole moment of this D state. And in fact, if we get a shift of about a kilohertz, which is, we're trying to get down to millihertz, and so this is a big problem. Now, in fact, it's not as bad as I indicate here, because if you choose the quantization axis appropriately, you can find an angle where, in principle, the shift goes to 0, but you have to control that angle. So this is why, at least for these first experiments, we're just thinking about single ions. So let me jump a little bit and say just how some of these simple ideas of quantum information can be used in our clocks. More recently, that we've been thinking about aluminum ions, and this project led by Till Rosenbad and now taken over by David Librant. The aluminum turns out has a nice transition we could do, this intercombination transition. Lifetime is about 20 seconds, so it's 200 times longer basically than mercury, so in principle we can get to longer resonances. And in fact, in principle, we could detect it the same way we do with mercury. There's a loud transition, this transition up to the singlet P1 level. Unfortunately, that transition in aluminum is at a fairly short wavelength where we simply we can't easily produce that radiation. So the idea that we've been using in this experiment on aluminum is to use some simple ideas from quantum information. And so Reiner just described how if you could say cool or what we do it anyways, we take our clock ion and install in this case magnesium ion in the same trap potential. And we can think about the normal modes of this kind of pseudo diatomic molecule here. And Reiner described how you could, first of all, you need to cool down, as Serge described that this morning in terms of optical pumping. Basically, we can pump into the ground state of motion. So that would be, after we drive the aluminum transition, we would use the magnesium ion to put the atom in the ground state of motion, say for either the stretch or the mode of motion. And then the basic idea, as Reiner described, is we can drive sideband transitions, so we can map the superposition state of the aluminum onto a superposition state of the motion of one of the two modes, either the common mode of motion or the opposite mode of motion mode. And then we basically just reverse that process, map that on to a superposition state of magnesium, and it turns out the wavelength there for we could use this fluorescence detection is a lot easier to handle. So this is the method we've been using to detect transitions in this aluminum clock ion. So there's a lot, there's a lot of nice extra features about this. First of all, the one we used in some of the early experiments, during when we're driving this transitions, we got up to times on the order, probe times on the order of about 5 seconds. But during that time, I'll say a little bit more about this later, the ion is heating due to noisy electric fields in the system. And so we can actually keep the laser cooling on the magnesium ion to keep the system cool while we're probing this transition. And the reason we can get away with that, this wavelength is quite a bit different than any transition wavelength in aluminum, so the stark shifts from this cooling laser can be made extremely small. Anyway, so that's one potential advantage. It turns out also one of the effects we have to calibrate in terms of getting the accuracy. We have to calibrate out the shifts due to the quadratic Zeeman effects, basically. And these are hard to measure directly, but it turns out magnesium has a fairly big shift for this B squared, so we can actually calibrate it with measuring on magnesium, and then we know what it is for the aluminum ion. The other thing is, one thing that's nice side advantage of this technique is that basically we have to worry, this system is at relatively high vacuum to about 10⁻⁻⁻ torr, but we still have to worry about the collisional frequency shifts on the aluminum ion. And so one of the things, I mean, we don't, most of these collisional shifts are not known, so we assume the worst case, that it's a pi phase shift per collision. And one way we can put then a limit on the frequency shift due to collisions is that we just need to measure the collision rate and then assume this worst case. And one nice thing about this pair of ions is that we can adjust the potential for where they want to trade position to be just a few Kelvin. And so these experiments so far are done at room temperature. So almost any collision with a background gas with 50% probability will cause the atoms to switch places. So we get a nice measure of the collision rate that way. And I won't say, there's a couple of other advantages. It turns out we can repeat, of course, this measurement process, and so it's what you might call quantum non-demolition. There's certainly imperfections when you do this mapping. We can repeat it to increase the detection efficiency. I just want to say also now this idea that D.D. Leibfried in our lab was always wanting to try to apply this to magnesium, or pardon me, to molecules, and those experiments have now been done. This is a paper by Pete Schmidt's group, and this is James Chow and D.D. and others have done this applied to molecules, and I won't say much more about that, but this opens up a lot of possibilities for doing molecular spectroscopy on ions. So let me just say, kind of give the status of clocks right now. And so the aluminum ion, we held the lead for a while, but we're certainly not in the lead anymore. There's been an experiment at PTB, and they've gotten this is now the systematic uncertainties, gotten down to about 3 parts in 10 to the 18th in those experiments. Now clearly, all the experiments so far have been done on single ions, but we want to get up the number. So we'd like a very long string of ions like Reiner's shown. Unfortunately, this quantum logic spectroscopy won't work. It actually made it work on 2 o'clock ions, but to scale it up to a large number would be hard. So we really like to be able to do the detection like we've done in mercury. And actually, this paper here is from Tanja Milstoibler at PTB, and she's shown how you can really beat down the systematics and also increase the signal to noise in these long strings. And then of course, I would say the leaders right now are the neutral atom experiments, and I'm just going to show a couple examples here. That it was, I think, Katori in Japan who first came up with the ideas here. Well, I should have said first, the idea of confining neutral atoms is this idea of optical lattices, and I think he was probably the first person to point out you can choose the wavelength of the optical lattices so that there are stark shifts from these potentials on the two states of the transition you might want to use for the clock. But if you choose that wavelength appropriate, the so-called magic wavelength, then the stark shifts are equal, so you can get rid of to suppress the stark shifts to a very high degree. Now, in fact, it's much more complicated than single stark shifts. There's scalar and dipole and tensor stark shifts that people have to worry about. But nevertheless, this basic idea works. And for example, Jun Yi's group has probably got the highest performance. They've gotten the systematic uncertainties down to about 2 parts in 10 to the 18th. And they recently had a paper where this statistical measurement, fractional precision, they show it scales as this factor times the inverse square of the time. And this, I think, is the record right now in terms of signal to noise to be able to do these measurements. And again, with apologies, there's many other groups working on these ion clocks, particularly the optical clocks these days. So let me come back now to quantum information, and it's just, this is one example of how we might improve the measurement precision. So there's two closely related ideas here. I'll try to give an idea. But anyway, of how they work. But anyway, we're going to think about Ramsey spectroscopy again. Instead of the simple pi/2 pulse applied to all the atoms, we're going to apply some entanglement pulse, which from a state where all the spins are down, we create this equal superposition of all spins down and all spin ups. This is a generalization of what Reiner talked about in the 2-qubit gate. And we can do that with a certain level of fidelity. But one of the key ideas is after we create this superposition, the phase of this wave function doesn't, now it increases as n times the oscillation frequency times the Ramsey time. So one way to view this, we've converted this n atoms into a kind of a single superatom where it's given by a superposition of the two states of the superposition state are given by there. But it's like the atom is oscillating n times faster than a single atom. I'm going to say a little bit more about that in a second. This is where the gain comes from, this much faster evolution of this phase. The idea is just as Reiner described, one way we can measure, do the measurement on after we apply the second pi/2 pulse. In this case, we could either do a simple rotation, as we did in the traditional Ramsey method, and then measure the parity. The other version of, and again, that's what I already said that, but there's another version that we actually first played with in our lab. It turns out it's not as robust as maybe the parity measurement, but it was more straightforward to implement. And that is, the second pulse, we would apply the same entangling operation again, and it turned out in the ideal case, without any errors, then before we do the measurement, the atom, this kind of superatom comes out to be a superposition of the all down and all up state with these coefficients here, where we've got this factor of n in the expression there. To give you an idea where the gain comes in is that this is a case cartoon of how ideally it might work for 6 atoms. So in the traditional ramp experiment, again, we're going to, in this case, the measurement operator changed a little bit. It's the number of atoms in the up state minus the number of atoms in the ground state, but the features are just the same as before. So the red curve is the traditional Ramsey method. And of course, again, the signal is given by this slope here. The noise is given by the projection noise, which for n atoms is given by this error bar here. Now with the entangled state, this for six atoms, it turns out that the slope turns out to be exactly the same. And you might say where the gain comes in is the fact that the noise is smaller. It's basically you're only measuring these two conditions, so the noise is smaller. And that's one way to say how this gain comes in. Of course, that's the perfect experiment. And more realistic experiments, here we did an experiment where we used up to 6 atoms. And the basic idea, Reiner pointed this out as well, you can see, well, here's for a single atom, for 3 atoms entangled. The key thing is that the phase is evolving three times faster, and also the slope is increasing as the number of atoms. And we get down to 6 particles here. You can see how the phase is evolving even faster, but the signal has gone down because the contrast of the fringes has gone down. There's nothing magic about this. In fact, in this experiment, the fact that we were losing contrast was caused by spontaneous emission due to the fact that these were on stimulated Raman transitions, on microwave transitions. But the basic idea is there. Anyway, it turns out that you win on signal to noise. You may not be able to realize the full gain, this so-called Heisenberg limit that I ideally described in the previous slides. But it turns out you win if the contrast is bigger than the square root of the number of atoms. And so we realized that in all these cases with up to 6 atoms, but only slightly, only a slight win for 6 atoms. And in fact, Reiner's experiment, he mentioned it briefly. They got up to 14 ions. And anyway, so these basic ideas for clocks, I think they're there, and I think they're going to come into play. But so far, in terms of these were kind of demonstration experiments, but they haven't really yet been employed in a clock, but I think they will be. There's another related idea, which many of you in the audience have heard about. It's called spin squeezing. Whoops. And it turns out it can be implemented by the same, these spin operators that I mentioned before. But anyway, the picture is a little different. It's not as, at least in principle, not as good as these ideas I described here, but it's a bit more robust than what I described. Let me not, since I've run out of time, let me just jump onto some. Let me briefly describe one. One quantum detection method is, I've described how we do displacements in phase space. Now, if we make the force frequency equal to the motion frequency, then in phase space we just displace the state out on a straight line. If we reverse the phase by pi, the wave function comes back, and of course the subtended area of that trajectory, that total trajectory, is 0. But if, for example, there's some small additional displacement in phase space before we do the translation back, then we pick up an area which, just as we realize we pick up a phase for the phase gate, we could use that. I use an example from Reiner Blatt's group. I like this, where they've basically made a superposition, a cat state, where in this case the spin is in the x direction, and the displacements are equal and opposite for these two x direction states. And then if in this case they were measuring a kick from a single photon, so if there's a photon that comes along and kicks the atom, then when they close the loop back and look for the interference on this, of the overlap parts of the motion wave packet, they can pick up a phase which allows them to see single photon kicks from spontaneous emission. And there's some related experiments on this, which basically incorporate very similar, this space idea. Anyway, but now the experiments have gotten down where you can measure displacements that are much less than the ground state wave function spread of the mode of interest. Okay, well, anyway, I was going to say a little bit about scaling. Let me just say that the basic idea that many people are pursuing is to make in this case, this is a trap structure that doesn't look like this idealized case. All the electrodes in a plane, but basically the atoms are suspended along a line above the surface of the trap, and it mimics the same potential that this would generate, but all the electrodes in a plane. And this is one way we're thinking of scaling up. That is the idea. In principle, we could put a large group of ions in one trap, and one reason we don't do that is because for n ions in a single potential well, there's 3 n modes, and after a while, the density of the modes, mode spectrum density becomes so dense that we can't isolate a single mode we want for a single gate. Let me just say a couple of other things. We're trying to take advantage of some of the techniques for very sensitive photon detection using superconducting meander line detectors, and this is a project we work in our labs. I wanted to say we benefited from Sebastian Bordedoc, who's here in Hong Kong. He has a company that's developing computer control for our experiments, and actually this is a quite general thing that is applicable to ion experiments, but many other experiments as well. One thing let me say is that a ubiquitous problem we all have, particularly for these small traps, is we see heating of the ions, which is bad for the gates because we want to be able to precisely control the motional modes of the gates. And I won't say much to say except that this we call anomalous heating because we don't understand it, but the idea is that it's stuff on the surfaces. That's pretty clear because when we clean the surfaces using argon ion beams, we can dramatically increase it. But we want to try to figure it out. And so in our group, we're collaborating with another group at NIST to bring up samples close to the ion where it's being treated in different ways. There's a review of the experiment, all these heating experiments done by Michael Brand, who's also a nearby neighbor here, who wrote this review when he was in Reiner's lab. Anyway, I just want to give you a couple ideas of the other types of experiments. A couple of very popular ones, so this one's it's already been mentioned. We use superconducting qubits, which can be made into with other elements. They can be made into artificial atoms, and there's the connection between what the ions in is not so much different. Here's a picture of an experiment from the NIST group where basically here's one qubit, here's another one, transmon qubits, but they're coupled by waveguides, which you can argue are very similar to the motion in the ion traps. And so there's many groups doing that sort of thing. There's also the idea of quantum dots where electrons in a two-dimensional electron gas can be brought into close proximity, making states which are usually states of 2 electrons in these traps that provide a qubit. But I like this example because in some ways it's similar to the kind of ideas we're trying to realize with ions, where even in some experiments they're moving electrons around with the idea of building a larger array. So let me just conclude by saying, speculating a little bit what's in the future. I think, I would be a little more cautious even than Reiner. So far, the ions are in the lead in terms of suppressing 2 qubit gates, which is the hard part. We're down at a part in 10 to the 3. This has been achieved in Oxford lab, our lab, and I just learned today in Reiner's lab, the kid down to this 10 to minus 3 per gate error level. But we still need to do a lot, and we have to get rid of some of these silly problems like and heating. And of course, for large-scale things, we have to invoke error correction, and so that's often the distance. Reiner's talked a little bit about simulation, and I think many of us feel that's the real application long term. And what about a factoring machine, which got a lot of this going? I think, I guess the factoring problem, at least for cryptographically interesting factoring, I mean, it's such a large, it's the hardest problem anybody's thought of, and I think probably, it's very likely by the time, even if there's a factoring machine coming up that could invoke Shor's algorithm, I mean, the cryptographers are very smart people, and they already have codes which, as far as even Peter Shor will admit, might not be crackable with a quantum computer. I've given you some ideas of the ideas for metrology, and there's now, of course, significant interest in companies. And this is Chris Monroe and others have started a company trying to make a device that they can get out for anybody in principle to use. And with that, I'll stop and acknowledge the group members and our lab director, during the time most of these experiments were done. So thanks.
Thank you very much, Dave. I guess we have some questions. Do we? Serge.
So Serge's question is, can we build up a number of ions to be maybe like what the neutral atom experiments could do? I think it'd be hard to get up to the numbers they talk about. I mean, Jin Yi and others, they're working with 10 to the 3, 10 to the 4th atoms. And in principle, we could make a long string, but I think, it's the size of this thing is going to be bigger than typically you might find in an optical lattice. So I don't know whether we can compete on that in the same way. It's still not so clear. I think it's not, they have their systematic shift problems, and we do. And I think there'll be a place for both systems as we go on. Maybe there'll be an obvious eventual winner, but I don't think it's clear yet. So.
Arnaud?
So it may be a silly question, but when I look at the numbers for the neutral atom clocks and the ion clocks, then they are pretty similar. Now, is that just because you try hard until you're as good as the other one, and then, or is there something deeper?
Well, first of all, the stability, with this fractional statistical precision is much better in the neutral atoms than in the ions, just because of the numbers, I would say. So if I maybe gave the wrong impression, but they're quite a bit ahead in terms of this statistical measurement precision. And as I say, in terms of the systematic precisions are about the same for ions, and I don't, you can argue who might be the ultimate winner. We all have our problems. So. I think there was another question back there. Yeah.
In the first part for your quantum gate,
I'm sorry?
for the quantum gate,
Uh-huh.
it seems like the gate operation depends on the ion rotation frequency.
Not, in principle, not so much the frequency. I mean, that gets in practical ways. But it mainly, there's many practical issues. You want to close this loop in phase space, and there's fluctuations on that. So, but the first order, it doesn't depend on the frequency. Now, in fact, you'd like to use, in principle, you'd like to use very high frequencies. Everything goes faster as the mode frequencies go up. So that's certainly one reason you'd like to go high frequencies. But the first order, it doesn't depend on the actual frequency.
Okay, Christophe, if the question is very short, because we are running out of time badly.
Are there people who have done error correction on the 2-qubit gate?
Yes, I think several of us have done it. There's simple demonstrations of 2-qubit error correction schemes. We've done it, other groups from Reiner's probably done it. Several groups have done that now, but it's just sort of a toy thing, you know, not really useful yet. So,
Okay, but what's the perspective? You mentioned 10 to minus 4 required. Do you think this will be done by error correction or by working better on the...
well, I would say that you know, to be careful, I would say to get to the next round of kinds of experiments, you'd like to get to 10 minus 4 to be able to do any sort of, you know, fairly sophisticated error correction. There'll still be errors in it, but at least you can, I mean, this is very, very gray area, but that's my feeling where, just to get to the next stage, you'd like to get to about 10 minus 4 errors on the individual operations.
Okay, so I think it's time to thank Dave again for this talk.